MiniExam for demo. So this first question is about a particular data set. So we have data on student study hours per week, and then we have final exam scores. And what we're trying to do is test whether students who study more have higher exam scores. The order of the questions is to start with the statistical model and then maybe sketch the model itself. But I'm actually going to start with the picture and then write down the model. So, my question here is whether those who study more have higher exam scores. So I'm actually going to put exam score on the vertical axis. And then I'll add study hours on the horizontal axis. So then my main question with this statistical test is, is there a positive relationship between these two things? So that might look something like this. Okay, so then if I'm going to write the model down, I want an equation that matches this relationship. So I have a couple of fill in the blanks here. So we have our outcome variable, which in this case is the exam score. So exam, and then I have some entry with a plus. In this case, that's just going to be the beta, so beta 0. And then I'm also going to have my beta 1. So we have beta 0 plus beta 1 times study hours, which is our x value. So study. And then this last bit is just the error term. So it's like the difference between the model and the data point. So, just our epsilon. Wow, that really is messy. Okay, so nice. So that's done. And then for C, what part of your statistical model would indicate a positive a relationship exists? Well, in this case, it would either be that beta 1 is positive or beta 1 is negative. So in this case, I'm just going to say beta 1 is not equal to 0. But when we're thinking about this question, we generally would expect it to not be negative, which would say like the more you study, the lower your grades, which I guess could happen if there's, if the exam is easy for some people who don't need to study, but then very difficult for other people who study but still end up not quite doing as well as they had hoped. Okay, so nice. So that's the first question. For the second question, we have you want to test whether those with a college degree have higher salaries. So again, a similar kind of question, using a data set with the variables college degree. So this turns out to be a binary indicator variable or a binary categorical variable, and salary. So this is in thousands. So again, I'm going to set up the model here visually first. So on the vertical axis, I want salary. And then the horizontal axis, I want college. And I'm going to have a 0 and a 1. So this is no and yes. And then we have data that corresponds to these two groups, just a bunch of salaries. I'm going to draw this as I would expect it. And then we'll set up the model. So we have two groups. I would expect those with a college degree to have higher incomes. And our model would just be basically a test of whether the means are different. So to write this statistical model down, we want college degree to be our predictor variable. So we have beta 0 is our intercept term. So this is 0 on the horizontal axis. So that will be our intercept. And then we have plus beta 1, which is, the slope of this thing. And then we have our predictor variable. So this is college degree. And then we have our error term. Nice. So the difference between the model and the data. Nice. So then our outcome variable is salary. So this is salary. And then we'll sketch it over here. Nice. And the important things here when we create these sketches is that we have the axes labeled and a nice visualization, and then the data itself. We don't know what the data is, so anytime you do this is just a guess. All right, so question 3, researchers studying whether those with more years of work experience measured with this variable experience earn higher hourly wages using a sample with 200 workers. The progression for output looks like this. And what we're trying to do here is write down that has been, and then try to interpret something that's telling us. So let's sketch out the model. So here we have work experience being predicted, hourly wages being predicted by experience. So experience is on the horizontal axis, and then wages is on the vertical axis. And it looks like from this picture, we have a intercept of 12. So it's positive, and then we have a positive slope. So our data is going to look maybe something like this. We don't know what the data is, but we do know what the model is. So this is our beta 0, and then our beta 1 is equal to 0.75. Okay, nice. So this is the model. And then what we're going to do here is interpret what the intercept term is. So the intercept is always going to be the average at an x value of 0. So in this case, we're saying 0 work experience, the intercept. And on the vertical axis, the intercept is wages. So we would say wages for workers with no experience. And then we could say is 12. And we're not given any context about the units here, but you can infer that this is dollars, although really we aren't given context. Okay, and then for the third part of the question, we're interpreting the coefficient of experience. So that's this one. And in this case, this is the slope coefficient, so it's the rise of a run. So we increase by 1 unit. How much are we going up on the vertical axis? So we're saying for every additional year of experience, how much additional wages are we getting? So in this case, we can say wages increase by 0.5 for every additional year of experience. Nice. Apologies for the handwriting. Okay, so this is pretty good. With the model, we have some interpretation of what the model is telling us. This question hasn't asked about p-values, but we're about to do those things. Okay, so for part 4, consider the p-value of 0.120 for work experience. This is this number here, which is the p-value on work experience. Wait, complete interpretation of this p-value. What exactly does it tell us? Well, in this case, the p is the probability. So it's telling us if we were to repeatedly draw under the null hypothesis of no relationship between these two variables, default null, we would see the extreme or greater, about 12%. So what we're saying here, p-value is if there was no relationship between the wages and experience, we would see a slope at least this extreme, roughly 12% of the. So this is telling us under the null distribution around 0 relationship, which is our default null, we were just randomly drawing that distribution, we'd see something like this only about 12% of the time, 12% of the draws we would make. This is not a probability on the truth. This number here is our best guess, but the truth is the sample that we draw from the truth. That is the randomness. So we're centering the null distribution on 0, which is the null hypothesis, and then we're checking how consistent is that with what we're doing. Here, it's not very consistent. So for B, we're checking the null hypothesis that experience has no effect on wages. And we're using this, so this is the confidence. And here, even though we're pretty confident, we have 12%, 0.2, 0.12, so our p-value over then even though we're that confident, the standard rejection region is even more confident. So if we're using a null hypothesis and this alpha, we do not reject the null hypothesis. So the answer is no. This is even more confidence than what we actually have. So this is part C. We would say alpha is, alpha is this alpha requires even more confidence than we have. Alpha is less than P. Okay. So something along these lines would work in this case. So for question 5, draw the sampling distribution for the null hypothesis. Label the axes, mark where observed coefficient 0.75 would be shaded in the values for the p-value. Okay, nice. So on horizontal, we have our data walls, and we're going to so large size. Remember that the sample size is very low. So the distribution here is approximately 1. We have our null hypothesis of 0, and actually observed is 0.75. And so our p-value is made up of this part, but then also on the other side we have negative 0.75 is this region. And together they make up 0.12. So 20 is 0.06. 0.06. question 6. A student lists the test by students who live off campus on different GPAs using around 100 students. And then we're given a bit of information about what the averages are. So for the first, students living on campus have an average GPA of 3.2, and students who live off campus have an average GPA of 2.9. So none of this is causal. We don't know either, but if we see this, we would be interested in knowing the difference. Okay, so then the question 6A, if we code on campus 1, so the question doesn't ask for a picture, but I often think of these things in pictures, so it can be helpful. So this is 0 for off campus, 0, and then on campus for 1. Okay, and then we see the average of this group is off campus group is 0.9, and then on campus group is 3.2. So 2 groups, and then we're trying to find a difference. So beta 0 represent this model, so this is beta 0. So beta 0 in this case would represent the average GPA of the 0 group. It's always going to be the vertical intercept, which is where the model hits the vertical intercept at 0. Okay, so in this case, this is the average GPA of off-campus, which in this case we know exactly what that is, and it's 2.9. Okay, then for B, what would beta equal based on the information given? Well, beta 1 is this slope, so it's the rise as unit out on the axis. So we're going from 2.9 to 3.2. So this 3 minus 3.9 is out to be 0.3. Okay, so beta 1 is equal to 0.3. So that gives us a number here. So this includes the 4 data. And I will see you in the next one.